they say the force of attraction, between a minus 40.0 microcoulomb and a positive 108 microcoulomb charge is 4.00 Newton. What is the separation between these two charges? And of course, in this problem, the force of attraction between a minus 40.0 microcoulombs and a 108 microcoulomb charge is 4 newtons. What is the separation between these two charges? So we're going to apply the Coulomb force here, the equation of the Coulomb force. So you have here one negative charge with a magnitude Q. We're going to call this Q sub 1 equals to minus 40.0 microcoulombs. On the other side, we have one positive particle, and this positive particle have a magnitude Q sub 2, and this magnitude Q sub 2 is positive 108 microcoulombs. And then we know that there is a force, that in this case would be a force of attraction, of course, right? The force F, of course, we know that is related to the distance between these two particles, not only to the magnitude of the charges of the particles, but also to the distance R or D between these two particles. We know the force, so we know that the force is just 4 newtons. And then we know that what is unknown in this problem is just the distance between the particles. So if we apply the Coulomb formula, or the Coulomb's law, we will have that the force of Coulomb is equal K sub E absolute value of Q sub 1 times the absolute value of Q sub 2 divided by the square of the distance. What we want to do here is to calculate the square of the distance, so I will multiply the force square of the distance. What we want to do here is to calculate the square of the distance, so I will multiply the force, that means I will multiply both sides by the square of the distance. So we say that the force times the square of the distance is now equals to the Coulomb constant absolute value of Q sub 1, absolute value of Q sub 2. So I will divide now by the force. So when I divide by the force, I say that the square of the distance is equal to K sub E, so the Coulomb constant Q sub 1, Q sub 2 over the force. So we can say that basically the distance between the two particles can be calculated as the square root of K sub E, the Coulomb constant absolute value of Q sub 1, absolute value of Q sub 2 divided by F, right? So R would be the square root of Well, what is the magnitude of, in this case, uh, Q sub E, the Coulomb constant? We know there is 8.99 times 10 to the 9 newtons meter square per Coulomb square times the absolute value of, now let's see this, we have minus 40.0 microcoulombs. So 40.0 microcoulomb, the prefix micro means 10 to the 6, 10 to the negative 6, sorry. So negative 40.0 microcoulombs is the same that negative 40.0 times 10 to the negative 6 coulombs, because mu, which is micro in the international systems of Unix, is 10 to the negative 6. And then these positive 108 microcoulombs are going to be 108 times 10 to the negative 6 coulombs. So we have to work with the values in coulombs, so we cannot work with the microcoulombs. We need to work with the values in coulombs. So I will say here my absolute value of minus 40.0 times 10, sorry, 40.0, I just said 4.0. So 40.0 times 10 to the 6 coulombs times the absolute value of 108 times 10 to the 6 coulombs. All this divided by the force, that would be equals to 4.00 newtons. 4.00 newtons. So when now you work, this is 10 to the negative 6, right? 10 to the negative 6. So when now we work, with all these numbers to solve this equation, you can find that the distance to separate this would be approximately, of course, remember that you will cancel the newtons that you have here, these newtons with these newtons. You will cancel out, right, these Coulomb squares with this Coulomb times this Coulomb. The absolute value of negative 40.0 times 10 to the negative 6 will be 40.0 times 10 to the negative 6, so positive 40.0. And then, well, when you multiply all these numbers and you play with the numbers that are in, the powers of 10, the different powers of 10 you have, so you have 10 to the 9, remember, times 10 to the negative 6 times 10 to the negative 6. This is the same that 10 using the powers, the property of the exponents, right? This is 10 to the 9 minus 6 minus 6. So this is basically 10 to the negative 3. What are we going to get here on the top? So when you multiply these numbers and divide by 4 and then use this 10 to the negative 3, you will get that R is approximately equal to the square root of 9.72 meters squared, which is approximately then 3.12 meters. So what is going to be the distance between the two particles? The distance between the two particles would be approximately 3.12 meters, right? So this is just the distance between the particles. This is the first problem. As you can see here in this problem, we knew the force between the two particles, we knew the mass of the charge of the particles, and then what we want to do was just to find the distance between those particles. Let's see now a second. Let's see now a second example. In this second example, I will give you. Let me just clear the whiteboard. So you can remember that I'm recording the video. So if you need it, you can just copy this exercise later while watching the video. So let me clear the board so I can explain the next exercise. You can take a picture of this if you want, or a screenshot so you can later copy the exercise. So now look at the next exercise that I have for you. They say in this exercise, two coins carry identical charges. These two coins are lying two point 2.50 meters apart, 2.50 meters apart, on a table. So if each of these coins experiences, if each of these coins, sorry, if each of these coins experiences a force of 2.0 newtons, how large is the charge on each coin? So we have a different problem here, because in this case we know the distance between the two coins. We know also uh, the force between the coins. What we don't know is uh, the magnitude what we don't know is the magnitude of the charge on these coins. So let's see this problem. So what we know, they say that the two coins carry identical charges. So the two coins carry identical charges, so we say that Q sub 1 is the charge of the coin 1. Q sub 2 is the charge of the coin 2. So the charge of the coin 1 is equal to the charge of the coin 2, and then we say that it's going to be equal to Q, right? We say that it's equal to Q. Now, what we know that the two charges, we don't know if the charges are both positive or are both negative. You know, they don't say that. Okay, they say that are identical, but we don't know if are positive or negative. Let's assume that are just both positive at the end. If are both negative, uh, the calculation will be the same, except that then the magnitude of the charge will be at the end negative, but they don't say anything about it. So I would be assuming, you know, that they are both positive. So this is Q sub 1, this is Q sub 2. If they are identical, the forces are going to be forces of repulsion. We have force like this. And now we know that the distance between the two particles is just this one. So we know the forces. We know that the forces are equal to 2 newtons. This one is also equal to 2.0 newtons. And we know that the distance between the particles is just 2.5 meters. 2.50 meters. So we want to know the magnitudes of the charges, right? So we apply the Coulomb's law. So we say the force of Coulomb is equal K sub E absolute value of Q1 times absolute value of Q sub 2 over the square of the distance. But now, Q1 and Q2 are equal to Q, and we are taking both positive, so we can say that this is K sub E Q times Q squared over the square of the distance. So if I have that the force F is K sub E Q squared over R squared, if I want to solve for R squared, I will say that force, I want to solve for Q squared, but I will solve for Q squared, so we say that force times R squared is equal to K sub E Q squared. I will divide by K sub E, so we say that the force times R squared over K sub E will be equals to Q squared. So we say that Q is equal to the square root of the force times the square of the distance between the particles over Q sub E. So the charge Q will be, what is the force? The force we know that is 2.00 newtons times the distance we know that is 2.50 meters square over K sub E we know there is 8.99 times 10 to the 9 newtons meter square over Coulomb square. So the newtons are going to cancel out, the meters squared are going to cancel out, so we're going to get a square root of Coulomb square, which is going to be Coulomb, right? So you want to make the analysis of the units. So you have newtons, you have the square root of newtons times 2.50 meters squared will give you meters squared. Below you have newtons meter squared over Coulomb square. So you will, below you have newtons meter squared over Coulomb square. So you will cancel out, right, just to show you quickly the analysis of the units, this Newton meter square with this Newton meters square. So you will have, this is the square root of 1 over Coulomb square, which is going to be the square root of Coulomb square, which is going to be Coulomb, right? So when we do that calculation that we show you here, you're going to get that this is approximately 0.37 times 10 to the negative 4 coulombs, which is going to be, to rewrite this in microcoulombs, right? 37 times 10 to the negative 6 coulombs, and 10 to the negative 6 coulombs is microcoulomb, so this would be 37 microcoulombs, or 37.0 microcoulombs. So it would be 37.0 microcoulombs. Three-point charges are located at the following positions. At the following positions. So Q sub 1 equals 2.0 microcoulombs, is at x equals 1.0 meter. Q sub 2, which is equal to 3.00 microcoulombs, is at x equals 0 meter. And Q sub 3 that is equal to minus 5 microcoulombs, minus 5.00 microcoulombs, is located at x equals minus 1.00 meters. So what is the question is, what is the force? What is the magnitude of the force? What is the magnitude of the force on the 3 microcoulomb charge? The 3.00 microcoulomb charge. So this problem is a problem to use the superposition principle, because we have here 3 charges. So we're going to have a coordinate system. This is the y-axis and this is the x-axis here. Then we have one charge that is q sub 1 that is located 1 meter to the right of the x-axis, sorry, to the origin, to the right of the origin. So this charge here is going to be q sub 1, which is a positive charge. Let me so q sub 1 which is a positive charge, and is equal to 2 microcoulombs, and the distance from this charge to the origin is 1 meter. So let me just represent the distance here. It is 1 meter from the origin. We have the charge q sub 2, which is another positive charge that will be at the origin, right? So this one is q sub 2, is exactly at the origin. And q sub 2 is also positive and is 3.00 microcoulombs. Coulombs. And then we have another charge that is q sub 3 that I will represent with another color because it's a negative charge. And this one is q sub 3, and q sub 3 is minus 5.00 microcoulombs, and it's again at 1 meter, but in this case to the left. 1 meter by to the left of the origin, so to the left of q sub 2. Well, the question now is that we have to find the magnitude of the force on the charge of 3 microcoulombs, so we have to find the magnitude of the force on q sub 2, right? So the unknown here is a force on charge q sub 2 that I will call force 2 as a resultant, is what is the unknown. So now, what is the analysis here? Well, the force due to Q1, the force on the charge Q2 due to the charge Q1 will be a force of repulsion. So this force will be like this. So this one is the force that 2 hertz on 1, and this one will be the force that 1 hertz on 2, right? Because these two charges are going to repel each other. Now, the force that Q sub 3 hertz on Q sub 2 will be a force of attraction because they have different signs. So this force here, if the force, that 3 hertz on 2, what this one is the force that 2 hertz on particle 3. So what we want to do is to find the forces, on particle 2. So if we isolate the particle 2, we see how on this particle Q sub 2, we have the force that 1 hertz on this particle 2 pointing to the left, and you have the force that particle 3 hertz on particle 2 also pointing toward the left. So this is the force that 3 hertz on 2. So we have the two forces, and the two forces are pointing in the same direction. So we say that the resultant force on particle 2, so the force on particle 2 will be equal to the force that particle 1 hertz on 2 plus the force that particle 3 hertz on particle 2. So it says son of vectors. So I will find the force that 1 hertz on 2. So the force that 1 hertz on 2 would be K sub E times Q1, Q2 over the square of the distance between Q1 and Q2. So it would be 8.99 times 10 to the 9 newtons meter square over Coulomb square times the absolute value of 2 microcoulombs. Remember I say it's 2 times 10 to the minus 6 times 10 to the minus 6 coulombs. So it's 2.00 times 10 to the negative 6 coulombs. And then Q sub 2 is 3.00 times 10 to a negative 6 coulombs. And all this will be divided by 1.00 meters square. So you will get that the force that 1 hertz on 2 will be equal to, when you just multiply and divide, you will get 54 times 10 to the negative 3 newtons, which is going to be the same that 0.054 newtons. Now we can calculate exactly, doing the same thing, the force that 3 hertz on 2 and is K sub E times Q2 times Q3 over the square of the distance. So this would be 8.99 times 10 to the 9 newtons meter square over Coulomb square times Q2 3.00 times 10 to the negative 6 coulombs times Q3 negative 5.00 times 10 to the negative 6 times Q3 negative 5.00 times 10 to the negative 6 coulombs, all divided by the distance between 2 and 3, which is also 1 meter. And then when you do this calculation now, you get that for the 3 hertz on 2 is equal to approximately 135 times 10 to the negative 3 newtons, so is 0.135 newtons. So you found the force that 1 hertz on 2, the force that 3 hertz on 2. Now we know that both vectors have the same direction. So I can calculate now force 2, the magnitude of force 2 as just the total between these two forces, so 0.054 newtons plus 0.135 newtons. So the force 2 will be equals to 0.189 newtons. And as a vector, I can say that the force 2 is a force of 0.189 newtons. I can say west, or I can say just to the left. And this one is the force on the particle 2. And when we do this, vector addition here, we're using the superposition principle, right? Because we calculate, I separate the force that 1 hertz on 2, the force that 3 hertz on 2, and later we combine both forces, making a vector addition, right? The vector sum. So we found then the resultant force on 2. So this is an example of the use of the, in this case, superposition principle. Now, I want to solve one more exercise. In this case, I want to solve one exercise that is about uh, electric field. So I will clear the the whiteboard. So you want, you can take a picture now or a screenshot of this screen, because I will now move to explain the new problem. In this case, a problem related to the electric field. My next problem in this part is a problem that say that an atomic nucleus has a charge of plus 40 E. So 40 E is 40 times the charge of the electron, or the charge of the proton. So this is what is 40 E. So we say we have an atomic nucleus that have a charge of 40 E plus 40 E. It's a nucleus, so it's positive 40 times the charge of the proton. So they say, what is the magnitude what is the magnitude of the electric field at a distance of 1 meter from the nucleus. So what is the magnitude of the electric field at a distance of 1 meter from that nucleus? This one is a very easy exercise, right? Because basically we have a positive nucleus here with a charge of plus 40e, so 40 times the charge of the electron. And then we have one point over here, and this point is separated at a distance of 1.0 meter from the nucleus. Now, if we analyze what is the direction of the electric field at that point, since this charge is positive, nucleus is positive, the electric field will be leaving the positive charge. So the electric field vector is a vector, that is radial with respect to the point charge that is the nucleus, right? And it's just leaving the positive charge, so just pointing on this direction that I am representing here in red. Now, what we know in this case, we know the magnitude of the charge, we know the distance, so we know also that the electric field is the force F divided by Q, or is, K sub E by Q sub 0, K sub E Q over the square of R. So if I want to calculate this electric field, I have just all the information that I need. So I say that the electric field would be K sub E is 8.99 times 10 to the 9 newtons, meter square over Coulomb square times Q. That is going to be plus 40E divided by the square of the distance, which is 1.0, divided by the square of the distance, which is 1.0 meters squared. Now, what is E? Is the charge of the electron or the charge of the proton, that is 1.6 times 10 to the negative 19 Coulomb. So we say this is 8.99 times 10 to the 9 newtons meter square over Coulomb square times 40 times 1.60 times 10 to the negative 19 coulombs, because this is what is E, divided by then 1.0 meters squared. So E would be, when we calculate this, 5.76 times 10 to the negative 8 newtons per coulomb. Newtons per coulomb. This would be the value of E in this case.